All right, let's talk about these ligand group orbitals for an octahedral complex. So now we're imagining that we have a metal. Let's just with ammonias at each ligand group Okay. So the first thing we know that each ligand. So how many electrons do you think we're going to get donated from each ligand group?
From the ammonias?
Mm-hmm.
Don't they have a positive charge? Am I crazy?
Let me see. Did we already go through all these?
What do I have? I've got the individual ones drawn, and then we did the A1G.
Oh, okay. So we did the A1G. Okay. Now, because we're going to start getting into, because every ligand group does sigma donation. Okay. Some of them become strong field ligands by doing pi back bonding. So then there's also going to be pi donation. Everyone knows that my favorite is pi donation, but that's
everyone knows.
But okay. So, but if you look at ammonias,
oh, they have a -1, don't they?
No, they're neutral.
They're neutral?
Yeah. So NH3 groups.
NH3 groups. Okay.
So how many electrons do you think are going to be? Because this is going to start leading to what we call the 18 electron rule. And so, how many electrons do you think ammonias are going to donate to a metal center?
Like none?
No.
No.
Draw out the diagram of ammonia.
Is it going to donate that lone pair?
It is.
Okay.
And if I have an octahedral field, how many electrons is it going to donate? It will be donated in total.
12.
12. So 12 electrons will be donated from
the ligands.
Yep. Now you have your A1G. Let's look at the T1U orbitals. Okay, so then what we're going to get this. And this we're going to repeat for each spatial dimension. Okay, how are these points? Yeah, for this one, you don't see why. I'm going to face this way. I know it's like, how can you just face an orbital any way you want it to face? Well, because at the end of the day, these are all still approximations trying to explain what's going on. When the real accurate way to do this would be just to put the molecule together and recalculate the new wave function. Yeah, it's just. Okay, so this is our T1U group. Which for you, I have something coming up that's going to be difficult. It's the first time you've ever done something like this.
Oh, okay.
But you're going to find a universal constant from the beginning.
Ooh, okay. Okay.
And the first time you see it, it's something you're going to have to review. It's something we'll review again in another class.
Okay.
But it's just you're at that level now where it's time to like, no more like, here's a theorem, do just this little bit extra.
Sure. Okay.
Now let's look at our EG group. So our EG is going to have two orbitals or two orbital groups. Okay, so do our Z orbitals first. Remember in high school, whenever you're doing math, the X orbital was always the X axis was always the primary axis. In quantum mechanics and in molecules, the Z axis is the most important axis. Why? Well, because a bunch of people doing the math felt like that's the way it should be.
I think that's a lot of things.
There's one ligand set. And then the other one. Now, here's a question. Based off, well, okay, so you can end up in a tetrahedral configuration based off, steric hindrance and whatnot. What two ligand sets do you think are going to be the most important for these octahedral complexes? You have an octahedral at a 3D with a 3D metal. What's the other set that's going to be super important as you go to like a 4D, 5D metal?
Other than EG?
Well, within the EG.
Within the EG.
So here you see we have the octahedral field.
Right.
What else do you think we get as we move up maybe from a 3D to a 4D metal? Remember, you shift from octahedral to tetrahedral based off hindrance and interference. What do you shift to octahedral to what when you move up to a larger metal?
I move up to a larger metal, octahedral to what?
Yep. What symmetry does that field have?
I mean, it goes tetrahedral, right? Or
No,
do you
not
go with the
tetra-
planar, the
Square planar.
So, okay.
So our second EG is a square planar field.
Oh, okay.
Okay, there's our EG. So then, just like we did before, and I'm not gonna do this for everything because you can kind of put these together. We're gonna look at some bonding. We're gonna and start to get an idea of why certain energy levels are what they are. So some of them fit together real easy. Like if you go back up to your A1G ligand field and your A1G metal field, you'll see that all those lobes just kind of line up. If I now say, well, I'm going to take this, let's take the T1U field, and I'm going to put in both the ligand field and the metal orbitals, okay? Because you remember that orbitals of the same symmetry are going to have to form the bonds. You don't even necessarily need to do all of those, you'll get the point. So you have a ligand group. And then you have your metal group. You see, and they form those nice bonds. Okay. And now you could go all the way around the T1Us with this and get each one of those. Now, we start to run into some issues with, say, like our, let's look at our EG level, okay? Okay, so I'm going to look at that square planar field first. Let's see. No, hang on. Let me take a look here. What did I do? Okay, so it's kind of a square planar, kind of not. Okay. But so if we think of the EGs from the metal orbitals that we have,
Like for Z squared or whatever.
yeah, so let's see, we have D squared. I'm just trying to think. Let me make sense of these 3-week-old notes. Hang on. Well, let's kind of take a look at the octahedral field for the EG. Okay. This is a topic that I've been having to read because I'm rusty on it. Like, why do we get the certain energy levels we do? I'd rather just calculate the quantum energy levels and be done with it, but I have to make sense of it somehow. take quantum chemistry, you'll see that we actually have equations that can give us the energy of a quantum level. And then we can go, well, yeah, that one's going to be there above this one.
Okay, nice.
Instead of just, we'll have numbers instead of being able to go, well, this one will be above this one because of reasons.
That's such a chemistry thing to do.
Uh-huh.
Just say because.
Mm-hmm. So let's okay, so put a ligand field like this. Okay. Now around the center. And that's going to line up with the DZ squared metal orbitals. And do you have to draw them flat like that? No, you really don't. I just try to make them look different so you know that it's one's a ligand group and one's from the metal. Okay, so I mean we get a nice bonding setup. However, something else is going to start happening as we're doing this. What happens between all of these?
Anti-bonding.
Not necessarily anti-bonding, but like I mean, in a way, yes. But what is the more fundamental definition of anti-bonding? It's what do the electrons do in anti-bonding?
They like repel each
They
other.
repel each other.
Okay.
So you see how those are different phases, so they can't bond. So you're going to get a repulsion. And if you start going around and you start building up all of these different all these different orbitals, you're going to see like some of them have repulsion, some don't. But the more repulsion you get, of course, you're going to get higher in energy. This is why going between different days, like when slides get off, I'm like, which slide was it on? But you get the idea that if you start building these, if you put together your EGs, your T1Us, your A1Bs, you're going to start to see some of these repulsive effects come into play. And it's going to give you an idea of where the energy levels go so we can actually start to build the molecular orbital diagram for, say, the cobalt, the octahedral cobalt amine complex. Okay, so let's give myself as much room as possible. So I'm going to start way down here. Where next? I think there will be good. At least you'll get the ideas. It's higher energy. Okay. Now I need one a little bit higher. Now I'm going to need 3 in the middle. Already running out of space. Alrighty. And then maybe gap. I'm going to try to move these up as high as possible. Okay, then, oh, let's see. These are always fun to get in the right place. 1, 2, 3, 4, 5. Okay, so then these are going to line up there. Kind of get that one there. Okay, and I need another 5 over, kind of like splitting those two levels there. Okay, now I can start putting in, this is my A1G level, T1U, EG, T2G, and then of course you remember that every single level has to have its counterpart anti-bonding level. And again, you're going higher in energy really based off repulsion. Then, now you remember from your metal, even though that we're only, when we got to like a +3 for the cobalt, we only had d electrons in that valence level. You also remember that that valence level has 4p and 4s available. Okay, because that's the row we're in. So here, your T1U is your 4p, your A1G is your 4s, then your 3D are these 5. Then over here, for your ligand groups, your A1G, your T1U, and your EG. Now, okay, so let's think about this. This is a, what did you say this was? The cobalt 3.
Yeah. Then it's like the
It's a D6 complex. Okay, so how we're going to represent that is we're going to say 1, 2, 3, 4. We're just going to put 6 electrons in there. We know those other levels aren't going to contribute because they're empty after becoming a cobalt 3. And so, and then you're going to get a total of 12 electrons from over here. Okay. And you can already kind of see what we refer to as the 18 electron rule. But question though, the T2G, how is that going to contribute? What kind of level is that?
It's non-bonding.
That's your non-bonding.
Yeah.
Because you notice there were no T2G, there was no T2G symmetry in the ligand field. So that we're just going to get straight across. That's our non-bonding. Okay, now I will also tell you that this split here between your T2G, which for an octahedral field makes sense, your T2G and your EG, that's your delta O there, the T2G to the EG star. Okay. And so now let's start thinking about where everything goes. Okay, our A1G, okay, oopsie, make that right color. It's going to come down to there. Gonna get that. That's also gonna have to go. Your A1G star, your T1U. I have to go there. And down there, and then we have a T1U from the ligand group. And so yeah, this will be non-bonding. So that's kind of denote that. And then our 3D, okay, so I forgot to write in what these are. At our 3D level, we have our EG and our T2G. Okay, so that makes sense. Now let's see, EG is going to go to there. G is going to come down to here. Going to go there. Go there. Does that get us everything? I think that gets us everything. So here we have the molecular orbital diagram for our octahedral complex. This molecular orbital diagram is going to be common. So we did it for cobalt in H36. This is going to be common for your ML6 complexes. So as you look at some of the orbital symmetries of the metals and the ligand fields, you can draw them out and kind of place like, okay, well, this is why that one's going to be there, and this one's going to be there, and so on and so forth. You're going to see more or less repulsion. You're going to, the non-bonding always has to be higher in energy than any bonding, no matter what kind of repulsion you have. And then, of course, your anti-bonding levels are maximum repulsion, so they have to be up there. But you can see their orders are not intuitive, so you can play with the actual diagrams, saying, okay, well, this one's going to get more repulsion here than this one, and get an idea of why your ML6 complexes are in this order. And in particular, it's ML6 N plus. All right, complexes with metal-ligand pi-bonding. Okay, so you have your T2G orbitals that are non-bonding in the sigma regime. Those orbitals are now available to match up with orbitals from the ligands for pi interactions. Okay, so one of the interactions that can take place. Have you ever seen a d orbital do pi bonding?
No.
Okay. So you've seen two p orbitals do it. Now the way this is going to look is, say, metal to ligand, pi bonding. So we have a p orbital for one of our ligands, and this could be any one of those Ds. So they come at each other. The d orbital is kind of twisted to the side. Okay. And you'll get your pi interaction that way. And then, of course, another place that pi interactions are possible is, let's take a look at, and this is in particular for Pi-Acceptor Ligands, okay? So let's take a look at which one is. Yeah, so carbon monoxide is a Pi-Acceptor ligand. Okay, so just trying to. So I'm going to do this one, then I'll give you another one to see if you can tell me if it's a Pi-Acceptor or or purely a Pi-Donor. Now, I mean, all of these are Pi-Donors, but you can also get Pi-back bonding. Okay. So carbon, when you work these out, you're going to see you get, if you go back to Gen Chem, and we don't need to do this. Let's not do the sigma level. You'll see it's the 2s level doesn't matter. Let's just go to the 2p level. Carbon on this side, oxygen on this side. Do our pi level, sigma level. If you look this up, oxygen does not have significant sp mixing. Carbon does, but since we have carbon and oxygen together, the sp mixing will dominate. Okay, and then when you look at the electron configurations, you see carbon has those two. Oxygen is going to have 4 at the 2p level. Then you do your 1, 2, 3, 4, 5, 6. There's your p level molecular orbital diagram for carbon monoxide. And what you're going to notice is we have a pi star level available. For pi interactions. This is going to go from a pi star. So you're going to start putting electrons in there. It's going to be pi star for the ligand, but it will become a pi bond for the ligand to the metal. So you know how earlier the textbook was telling you that the ligands will lose one, like if it has a triple bond, it'll go to a single bond, and then you'll get pi, like a pi interaction with the metal.
Yeah.
This is why the metal is going to pi back bond into the pi star level, decreasing the bond order of the ligand, and then forming a pi interaction with the ligand. And so what we have is there's a pi star. So you're going to get pi back bonding into that pi star level, and you're going to use some of those p orbitals now to then form a pi interaction with the metal. Okay, now you tell me, let's use N2 as a ligand.
And
Do you think it's going to be a pi? And let's refer to these as pi donors and pi acceptors. Okay, so your pi donors are purely going to donate. Your pi acceptors are going to have this kind of interaction.
it's got 5 electrons.
Yes. So 2s2, 2p3. You only really need to worry about the 2p level.
Sure. I mean, I guess that's not going to do it.
Oh, it will.
It's gonna?
Will it be a pi acceptor or a pi donor?
Donor? Question mark?
Draw out the 2p molecular orbital diagram.
Okay.
Each nitrogen has a valence shell 2s2, 2p3.
2s2, 2p3.
So just go for the 2p level.
Yeah.
Why is there a feather on my note page?
It's part of the duck.
Inky mode?
What does that mean?
I don't know, but I'm afraid to click it. I'm afraid of inky mode. Oh, it brought the duck back.
Is the duck named Inky?
I don't know.
What does he do?
I don't. Huh. Can I click on him? All right. What do you do? Oh, he flies. He honks. Hey, if I put you up here, I make you honk at something I drew. Oh, he doesn't like that.
Oh gosh.
I don't know what he does.
Oh, okay. Well, I mean, I think I drew it. Like, I didn't draw the other side, but is that not like
You put too many electrons in.
too many electrons?
Yeah.
I thought I have 5.
You put the 2s electrons in the 2p level.
Dang it.
And so
Okay.
let's look at this.
So it's got like just like two in the pi star then?
No, so look, 1, 2, 3, 1, 2, 3, because your nitrogen is going to be okay. So your 2p3, we're only worried about those 3 electrons for each side, the 2p's. This is your 2p's, 2p orbitals. Then you're going to have your pi, your sigma level, pi star, sigma star. Keep in mind, it's been a number of years since you've done this.
It's been 1 year.
That's long enough. So I know you're the person who'll go home going, damn it!
I didn't remember that.
Okay, so you see how I have 6 electrons there?
Okay, I'm seeing it now.
1, 2, 3, 4, 5, 6, which makes this a Pi-Acceptor Ligand. Okay, did I put those lists on here? So we need to know which ligands are pi donors and which ones are pi acceptors. So your pi donors are going to give electrons from a filled ligand p orbital to the metal center. They lead to high spin complexes or typically your weak field ligands. Okay. Your pi acceptors will accept electrons typically into an empty pi star level set of orbitals. They're going to give a large delta O, and they're typically going to be strong field ligands. So, for example, make sure you get to change colors. Your pi donors would be like Cl minus, bromide, iodide, hydroxide. Tell me what this means.
Just the R is like some sort of carbon.
Yep, so, some sort of functional group. And then we have the R2N minus, O2 minus, nitride, and believe it or not, H2O. Your pi acceptors I don't believe these are exhaustive lists, so just we just showed like CO is one of them, cyanide is one of them, a phospho R3 group. That one of these, for example, is that PPH3 we were looking at.
Yeah.
plus, and then one that I thought would be fun for you, all alkenes.
All empty.
Now, we go down and we can look at some changes between Pi-Donor trees and Pi-Acceptor trees. Now, in the Pi-Donor tree, this is pretty much the tree we just did. It's just a little more spaced out. You can still see the T2G and the EG with your delta O. You can see that the T2G is going to have is going to still be non-bonding. This tree actually accounts for the fact that you can't have ligand groups that have T2G in them. But you're still going to get that. You're still going to get that single non-bonding. But as you move, so let's see. So now that we have, and this is in particular because now that we have pi donors, the tree we looked at before was sigma donors. Okay, this brings into the fact that we now have pi donors. Let's see. Now you also see the very huge delta O going to the Pi-Acceptor. You see how much greater that is. But kind of study these and think about Pi-Donor versus Pi-Acceptor, and look at the difference between the molecular orbital diagrams.
Okay. Well,
oh, I guess that runs us out of time. Let's see. Here's a little slide that can help you out.
yeah,
So this can help out. There's another slide that can help out. We're getting to the 18 electron. So the 6 Pi-Donor Ligands provide the 18 electrons that occupy these various symmetry levels. The 6 Pi-Acceptor Ligands provide only the 12 electrons that you originally saw. Now keep this in mind. D7 complexes are not favored. Are not favored due to a large delta, making it hard to populate the EG star orbitals. So it's really going to be hard to make these octahedral complexes, especially with Pi-Donor, Pi-Acceptor, with anything D7 and above. And then the 18 electron rule, which we'll talk more about next time. Low oxidation state organometallic complexes contain Pi-Acceptor ligands, and the metal center tends to require 18 electrons in its valence shell, filling the valence orbitals. And we'll take a look at that. So, like the thing about D7, for you to have a D7, let's even do low spin. Let's imagine a large delta O. There's 6 of them. I still have to have one up there, and that large delta O is really going to say no, not very favorable. Okay, so we will actually in the exercise we'll look at the 18 electron rule. You'll see how that works out. But these 3 slides here will combined with the textbook will help you really kind of suss out these molecular orbital diagrams for your octahedral complexes involving pi donors and pi acceptors.
okay. All right.
It's a lot of new stuff, but